All right, today we're going to dive into one of the cleverest breakthroughs in AI. It's all about how these tiny modular plugins are solving a massive problem for the world's most powerful artificial intelligence. This is really a story about efficiency, and it all starts with a pretty simple question.
So, this is the big one, right? The central challenge. Imagine you have this genius AI. It's a master of language. How do you go about teaching it a new, super specific skill, like, say, analyzing customer sentiment, without having to create and store a completely new, gigantic copy of the entire model?
So here's our roadmap. We're going to start by looking at what I'm calling AI's big cloning problem. Then we'll meet the hero of our story, the adapter solution. We'll put it to the test, comparing its performance to how many parameters it actually uses. We'll also see how it fixes a classic, frustrating AI problem, forgetting things. And finally, we'll wrap it all up with why this is such a game changer for the future of AI.
Okay, so let's set the stage. We are living in an era of unbelievably powerful, pre-trained AI models. I mean, they can write, they can code, they can reason like we've never seen before. But there is a huge hidden cost to all that flexibility. To really wrap your head around the problem, you first have to appreciate the sheer scale we're dealing with. The models at the heart of this research, like Google's BERT, they aren't just big. They are absolutely monumental in their complexity. So, the large version of BERT has 330 million of what are called trainable parameters. Now, what's a parameter? Well, think of it as a tiny little knob that the AI can tune to learn something. Now, picture a control panel, but with 330 million of those knobs. That's the machine we're trying to teach. And the traditional way to teach this giant new tricks is called fine-tuning. And honestly, it's pretty much a brute force approach. You have to take the entire 330 million parameter model and adjust all of those dials just to learn one new, specific thing. And this right here is the heart of the cloning problem. If you have, say, 100 different customers who each need the AI for a unique task, the old method forces you to create and store 100 separate, gigantic copies of that model. It's just incredibly wasteful. The dream, the goal, is to have one core AI that you can just add new skills to efficiently without all that duplication.
And that brings us to the solution, the really cool part of this research, a beautifully simple and wildly efficient method called adapter-based tuning. So what in the world is an adapter module? Think of it like a tiny new skill chip for the AI's brain. It's a small set of neural network layers that you literally insert into the existing massive model. They're designed to hold only the knowledge for one specific new task. And this is the most important part, the original model remains completely untouched. The process is just brilliantly simple. First, you take your big AI and you freeze all 330 million of its original parameters. They are locked, they cannot be changed. Second, you just inject these small adapter modules right in between the existing layers of the network. And third, when a new task comes along, you only have to train the parameters inside those tiny new adapters. The huge original model just sits there untouched. Now, the secret sauce that keeps these adapters so tiny is this clever bottleneck design. So imagine the flow of information in the AI is a wide 6-lane highway. The adapter briefly funnels all that traffic down into a narrow single lane, the bottleneck, where it can efficiently analyze everything before opening it back up to 6 lanes. This little trick allows the adapter to learn powerful new patterns using just a tiny, tiny number of parameters. Okay, so the idea is elegant. It saves space, it saves computation. But here's the billion-dollar question. Does it actually work? I mean, can these tiny little plugins really perform as well as retraining the entire behemoth? So, does this efficient shortcut come at a cost? Do you lose performance? Let's take a look at what the data says. The results are just stunning. On the GLUE benchmark, which is like a really tough exam for language models, full fine-tuning scored an 80.4. The adapter method? It scored an 80.0. That's a performance difference of only 0.4%. I mean, it is practically a statistical tie. It's incredible. Just look at the trade-off here. It's amazing. To get that almost identical performance, the old fine-tuning method has to train 100% of the model's parameters. With adapters, you get to that same level of performance by training only 3.6% of the parameters. You get almost all of the power for a tiny fraction of the cost. Now let's think about what this means for storage.
To teach the model just 9 new tasks, fine-tuning requires 9 times the storage space of the original model. With adapters, you only need 1.3 times the space. It completely changes the economics of deploying customized AI. It's a whole new ballgame.
But the benefits don't stop at efficiency. No way. This adapter method also solves another, much older problem in artificial intelligence, something researchers have been wrestling with for decades.
It's called catastrophic forgetting, and it is just as bad as it sounds. This is when you train a neural network on task A, and it gets really good at it. Then you train it on task B, and while it learns task B, it completely forgets how to do task A. It's like learning to speak Spanish and then suddenly being unable to remember your native language. It's a huge problem.
And adapters solve this problem beautifully because the core knowledge of the original model is frozen. It's locked in. It's impossible for the model to forget what it already knows. Learning a new task simply means plugging in a new adapter. That's it. So, where traditional models have this fragile, easily overwritten memory, an adapter-based model has perfect recall. Each task gets its own dedicated little module, so the knowledge from task A, task B, and task C can all coexist perfectly within a single AI.
Okay, so let's zoom out and look at the big picture. This isn't just some clever engineering trick. This has really profound implications for how we build and use AI from this point forward.
This really points to a future where AI is way more compact, with one base model doing the job of hundreds. It's extensible, letting us bolt on new skills anytime we want. It's scalable, which is perfect for big cloud services where thousands of customers have unique needs. And maybe most importantly, it's more accessible, lowering the barrier for everyone to customize these incredibly powerful tools.
The authors of the paper sum it up perfectly. They state that this method yields a single, extensible model that attains near state-of-the-art performance. It really is the best of both worlds, efficiency and power, all in one package.
So, this research gives us a brilliant answer to the how we can make AI more efficient and scalable. And that just leaves us with a final thought to chew on. Now that we have a much better way to teach AI, what are the most important things we should teach it next? Thanks for watching.